Okay, so we're continuing on chapter 17, which is basically electrochemistry. We kind of started last time talking about a little bit of a review, perhaps for some people, maybe not, in terms of redox reactions. Um, so remember that basically a redox reaction basically is an oxidation and reduction reaction that takes place. Those two things always sort of occur together. So again, if something gets oxidized and something does get reduced, um, when we talk about oxidation, there's a few different definitions of oxidation. Oxidation, normally what we deal with here in sort of general chemistry is the loss of electrons, while reduction is the gaining of electrons. So that's that Leo the lion goes grr or oil rig. There's a couple other definitions of oxidation and reduction that we don't really come across too much in general chemistry. But again, if you kind of continue on to organic chemistry, you'll will sort of come across it. Another definition of oxidation is the gaining of oxygen as you kind of go from reactants to products, and also the loss of hydrogen or H2 as you go kind of from reactants to products. So again, those are two other definitions of oxidation. Reduction also has similar definitions as well, basically the opposite. So reduction would be the loss of oxygen as you go from, say, reactants to products, or the gaining of H2 as you go from reactants to products. But mainly for us, we will probably see more of the losing and gaining of electrons in terms of oxidation and reduction. And we talked about sort of an easy way to determine if something's being oxidized or reduced. You could kind of just use like a basic sort of number line with like zero in the middle. And to the right is positive numbers, to the left is negative numbers. And really, when you do lose electrons and go through oxidation, you become more positive. So if you see yourself sort of moving on the number line in that positive direction, that means that substance is going through oxidation, and vice versa. Obviously, if you gain more electrons, you're going to be more negative. So if you kind of see yourself on that number line moving towards the negative side, um, that would mean that the thing goes through reduction. The other couple important things that we talked about as well in terms of that is the oxidizing agent and the reducing agent. So when you're asked about the oxidizing agent, it is basically opposite of the name. So the oxidizing agent is actually the substance that is getting reduced. And the reason for the name is, as we talked about last time, in order for that substance to get reduced, it has to cause the oxidation in something else. Thus, it is known as the oxidizing agent. And same thing with the reducing agent. The reducing agent is the substance that gets oxidized, and basically the same idea there for the name. Because it gets oxidized, it will lose electrons, and it will allow somebody to gain electrons and go through reduction. So again, kind of the simplest way, or maybe the easiest way to sort of remember the agents, if you will, is sort of opposite of the name. So if it's the reducing agent, it is the guy being oxidized. If it's the oxidizing agent, it's the guy being reduced. Now, those things are typically found on the reactant side of the equation. Your oxidizing agent, your reducing agent are usually found there. And we sort of finished up, I think, last time talking again about oxidation states or oxidation numbers. So remember that an oxidation state or oxidation number is essentially the charge the element would have if there was sort of a full transfer of electrons in that particular compound it's in. Um, and what ends up happening is sometimes the oxidation number or state is not the kind of normal charge, if you will, that we associate with an element. Sometimes when we think about elements and their charges, that's really for ionic compounds. So when those guys, a metal and a non-metal, sort of come together, we do get those transfer of electrons. So when we think about kind of normal charges, say something like nitrogen, we normally think of as like -3. And that usually is the case in an ionic compound. But if we have nitrogen in a more of a covalent compound where it's sharing electrons, it may actually take on a more positive sort of oxidation state, like maybe +4 or +3 or +5 or something like that. So again, when we do oxidation states, we are looking at sort of what the charge is in that particular compound for that element. And again, it may not always match up with sort of what you have in your head in terms of the charge of the element. When we do assign oxidation states, a couple of rules that we talked about. First one is pretty much anything that's uncombined in its natural state will have an oxidation state of 0. Then anything that's sort of a monatomic ion, anything that's sort of its normal sort of charge, like if you had iron 3 chloride, like we talked about, the iron would have a +3 charge, or oxidation state. Oxygen is a really good place to start. Usually that is -2, except if it's peroxide. And again, peroxide is O2 2 minus, and you would typically see that extra 2 on the bottom, usually in the formula, like hydrogen peroxide. Then it would be -1. Hydrogen is usually +1, except if it comes after a metal, then it's -1. And then basically, when you add up all of your oxidation states or numbers, that does need to equal the charge on the molecule or ion. And again, if there's no charge, then obviously it needs to equal 0. If there is some type of charge, you need to add up all your oxidation numbers, and it doesn't need to equal that charge. Important thing about sort of assigning oxidation numbers is you should not only assign the number, but you should include the charge. So if it's a positive oxidation state, you should include the positive. If it's a negative, you should include the negative. Again, if it's like -3, you can't just write 3. If it's +3, you can't really just write 3 because you don't know if talking about +3 or -3. So you do need to specify the charge. In addition, when you're assigning oxidation numbers, it is just for one of the element by itself. So for example, if you had something like 7 oxygens, you would say the oxidation state is -2, not -14. So again, individually assigned oxidation numbers for those elements. Any questions on that stuff we sort of covered here last time? Okay, what we're going to talk about next is sort of balancing more complicated redox reactions. And again, kind of depending on, I guess, maybe who you had for 50 or whatever it may be, you might have went into detail on this. You might not have went into detail on this. So again, we're just going to kind of go over it and make sure everybody is sort of on the same page, because you do need to understand how to do these things for sure. We talked about balancing sort of really simple redox reactions, because remember, you can't split it off into their half reactions. So we could have an oxidation half reaction, and we can identify the oxidation half reaction because the electrons are on the product side, like they're being lost or given off. We also have a reduction half reaction, and we could recognize that as having the electrons on the reactant side, like they're being gained. And when you have just really basic sort of redox reactions, pretty much the only thing you need to make sure of is the number of electrons in each of those half reactions are always the same number. So that may require you to multiply a half reaction by a coefficient, or maybe both half reactions to get the electrons to the same number. You always want the electrons to basically have the same number, and then you could add them together. The idea behind that is when we have an oxidation, we do have a reduction. So however many electrons are lost by something should be how many electrons are gained by something else. So they always need to be the same number, and they should always be on opposite sides of the arrows in those half reactions, because when you add them together, the half reactions, the electrons should always completely cancel out. So when we're balancing a little bit more difficult sort of redox reactions in either acidic or basic conditions, we do have to do a few additional steps rather than just kind of add them together. And we're going to go through this one right here, and we're going to balance it together and kind of talk about the different steps that you want to do and how to balance it. We're going to first balance this in acidic solution. So here we want to balance this here in acidic solution. So really the first thing you want to kind of do is, when you have sort of the unbalanced equation here, you basically want to split it off into its half reactions. So the easiest way to do that is really just take the two things that pretty much look related to each other. So clearly we have an iron with a +2 charge, and we have an iron with a +3 charge. Those two things are clearly related to each other. We also have a dichromate that has chromium in it, and we have chromium. So obviously those two things are related to each other. We also want to kind of maybe determine up front, because it's helpful to have the information of sort of what is being oxidized, what is being reduced. So again, we could just use a basic number line to sort of help us decide that. And if you become, again, more positive, you're being oxidized. If you become more negative, you're being reduced. So if we look at the oxidation number for iron here, it is +2. And if we look at it for iron 3, it is +3. So again, in terms of what is happening, we're starting at +2, which would be like right here. And we are ending at +3, which is moving in this direction. So we are obviously moving towards the oxidation direction. And that tells us that this would be our oxidation half reaction. By default, what that means is this guy here is going to be our reduction half reaction. And we could do it by looking at the oxidation numbers here as well. Oxygen being -2. There are 7 of them, gives you -14. Overall charge here is -2. Each of the chromiums here actually has to be +6. That gives you +12 and gives you -2 to +3. So if we looked at the chromium, it is actually starting at like +6 and it is heading to +3, which would be moving in this direction. And that means that we are definitely being reduced here. That also means that the iron 2 here is our reducing agent. And the chromium here, or the dichromate, is our oxidizing agent. Any questions on sort of how to identify all that stuff there? Okay. So once you've basically have split these reactions into their half reactions, the next thing that you want to do is just simply balance all the elements other than oxygen and hydrogen. So we're going to balance everybody but oxygen and hydrogen. We're going to balance it like a normal equation. So when we look at the iron, we have 1 iron of each on each side. So we're balanced. When we look at the chromium on the bottom, we have 2 chromiums on the left, 1 on the right. So we are going to put a 2 here, just like we would normally balance a regular equation. Now, once you've balanced pretty much everything other than oxygen and hydrogen, the next thing that you're going to do is to balance the oxygen. So after you balance everybody else, you want to balance the oxygen. And the way we balance the oxygens is we add water to whatever side basically needs oxygen. The goal is to get the same number of oxygens on each side of the half reaction. Now, when you do add water, you're not only adding oxygen, but you're also adding hydrogen. So for every water that you add to one side, you add 2 H pluses to the other. So chromium 3 is reduction doesn't. No. So when we look at chromium, in terms of where it starts, so just draw a new little curve here. So chromium on the left-hand side started at +6. Chromium on the right-hand side started at +3. So if you just kind of do it on the number line, +6 would be like here, right? And +3 is to the left, right? So it is moving to the left, right? It's becoming more negative and it's going through reduction. So that's why the chromium is going through reduction. All right, so when we add that water to one side, we're going to add 2 H pluses to the other. Again, that's going to balance our oxygen. That's also going to balance our hydrogen. So if we look at this here, in the terms of the iron has no oxygen, so we don't have to worry about it. On the bottom one, the chromium has 7 oxygens on the left, none on the right. So to the bottom half reaction there, we would want to add 7 waters. Again, because we added 7 waters, we want to add 14 H pluses to the other side. So we added 7 waters to one side, 14 H pluses to the other to balance everything. And I'm just going to kind of rewrite it one more time here just to make it a little legible, a little bit easier maybe. So top one, we really didn't do anything to it. Bottom one, we added 14 H pluses to our left-hand side. And at this point, once we balance all the other elements and we've balanced oxygen by adding water and adding our H pluses to the opposite side, we are ready really to balance the charge on each side. I will just take a note here as well. Sometimes before we talk about that, sometimes you do get a redox reaction where you're starting out with perhaps more hydrogens on one side than the other. And if you have that situation, you should add H pluses to the opposite side. So not in this particular example, but it is possible that you could kind of start out with maybe more hydrogens on one side than the other in a half reaction. And again, we could use H plus to help us balance them. So you would add the appropriate amount of H pluses to the other side. Again, you don't have to do that in this particular case because we didn't start out obviously with more hydrogens on one side. Now we're ready to balance the charge, and we want to balance the charge by adding electrons. So we're going to add electrons to balance the charge. Now, there's many ways you could kind of look at doing this, but really the simplest way is to just take the overall charge on each side. So if we look at the top half reaction, on the left-hand side, we have a grand total of +2. On the right-hand side, we have a grand total of +3. That means the right-hand side here does need an electron. The overall charge now on the right-hand side is +3 and -1 is +2. Overall charge on the left-hand side is +2. So they do not need to equal 0 on both sides. They just need to equal the same charge on both sides. So in this case, we have +2 happening on both sides of the arrow. Now, when we go to the bottom one, we have 14 H pluses. So really that is like a +14 happening. This dichromate overall charge is -2, which means it has a -2 overall. You could go individual oxidation numbers, but it is going to add up to -2 when it's all said and done. So why do all that work again? So when we do all this, we do end up with a grand total of +12 on the left-hand side. Right-hand side, we got +6 happening there and 0. So we have a +6. That means that to get them to the same number, we need to add 6 electrons to the left-hand side there. And that's 6 electrons plus the +12 gives us +6 on the left and +6 on the right. Now, by identifying earlier on what was our oxidation and what was our reduction reactions, we were able to identify that the iron was our oxidation reaction. So this is a good way to check yourself. I added electrons to the product side, so that makes sense because it's my oxidation reaction, while the dichromate was my reduction, and I added my electrons here to the reactant side, which makes sense for a reduction reaction. So that's why it's good to sort of have an idea as to which one's which. You will know when you add your electrons if you are adding them to the correct side, and you should never ever add electrons to the same side because they should always cancel out. Any questions up to there? All right. So now that we balance the elements, now that we balance the charge by adding electrons, we are ready to add these reactions back together. Before we could add these reactions back together, Again, the electrons need to be the same in both half reactions, and they are not in this case. So in this case, we have 1 electron in the iron half reaction. We have 6 electrons in the dichromate half reaction. So to make it even, what we're going to do is multiply the entire iron half reaction by 6. That will get us to the same number of electrons in each half reaction. So what I'm going to do then is I'm going to multiply that, and I'm going to rewrite it on the next page here. So taking that 6 all the way across in that iron one gives us 6 iron 2s, goes to 6 iron 3s, and 6 electrons. And the bottom one, we really didn't do anything to, so 6 electrons plus 14 H pluses, plus dichromate here gives us 2 of those guys and 7 of these guys. So now that we have the electrons the same, we can add these back together. And pretty much anything that is on opposite sides of the arrow, that's the same thing, can either completely cancel out or reduce down. So in this particular example, it is just the electrons, which should always cancel out. Again, they're on opposite sides of the arrow, and they are the same number. And then pretty much if that's the only thing that cancels out, we pretty much take everything on the left-hand side of the arrow stays on the left-hand side of the arrow. So we have 14 H pluses plus Cr2O7 minus plus 6 of our iron 2 goes to 6 of our iron 3 plus 2 of our Cr3 plus and 7 waters in this particular case. Now, if I did everything correctly here, this should represent the balanced equation in acidic conditions. So this should be balanced in acidic conditions. And what does that mean when it's balanced a redox reaction? Well, it means that it's balanced basically 2 ways. It is balanced like a regular equation, which means you have the same number of elements on each side. So if we quickly look through it here, there's 14 H's on the left, 14 on the right. There's 2 Cr's on the left, 2 Cr's on the right. There are 7 oxygens on the left, 7 on the right. There are 6 irons on the left and 6 irons on the right. It should also be balanced by charge. So it should have the same overall charge on the left-hand side and the right-hand side. So if we look on the left-hand side in terms of charge, there's plus 14 for our hydrogens. There's minus 2 for our dichromate. There is plus 12 for our iron. So that's a lot of math there, but that is plus 14 and plus 12 is plus 26. Minus 2 gives us a plus 24 on the left-hand side if we add up all of the charge. On the right-hand side, we got 6 times 3 is plus 18. We have 2 times 3 plus is plus 6. And we have 0 for the water. So that is plus 18 and plus 6 gives us a plus 24 on the right-hand side. So this would represent, again, the balanced redox reaction in acidic solutions. Any questions up to that point there? So again, just to sort of review the steps, we want to split it off into our half reactions. We want to balance all the elements with coefficients other than oxygen and hydrogen. We want to balance oxygen by adding water to whichever side needs the oxygen, and H plus or 2 H pluses for every water that we add to the other side. We then want to add electrons to balance out the charge on each side, and those electrons should be added to opposite sides of the arrow. We want to make sure the electrons are the same number in each half reaction, and once they are, we want to add them together, both half reactions, and cancel out whatever will cancel out. Any questions for those steps there? Now, this is the process for acidic conditions. Now, if we were talking about basic conditions and we wanted to balance this guy in basic conditions, there's a couple different approaches, but honestly, I think the easiest approach is to basically do it just like what we did. So if you were to balance this reaction in basic conditions, you might as well just go through all the steps we just did and balance it in acidic conditions first. Now, once you've balanced it in acidic conditions, what you want to do is an additional couple of steps. And the additional couple of steps that you need to do is, as you can see, because it's acidic conditions, we will have H plus in the reaction. In this particular case, we have H plus on the left-hand side, or you might have the H plus on the right-hand side, but you will have H plus in there somewhere because, again, H plus is an acid. This is acidic conditions. That's why there's an H plus in the total equation when it's all done. Now, because it's basic conditions, what we're going to do is add OH minus to both sides. So once you've balanced it in acidic conditions, what you'll do is add OH minus, not to one side, but you'll add it to both sides. And you may be asking, how do I know how much OH minus should I add? You should add an equal amount to the H plus that's there. So again, once you balance it in acidic conditions, on the left-hand side of the reaction, right-hand side of the reaction, somewhere there will be some H pluses like we see in this one we just did. So what you want to add is an equal amount of OH minus to both sides. So let me take the equation that we just had here that was balanced in acidic conditions, and I'll rewrite it real quick. So again, you would just follow all the same steps we just did to get to this equation. And in this particular case, we have 14 H pluses. So what that means is we are going to add 14 OH minuses to the left-hand side. And also, we'll put it over here to the right-hand side. So we're going to add it to both sides of this equation. Now, as you may know, when you have H plus and OH minus, those two guys like to make water. So the side that has both the H plus and OH minus on it, they will combine. So in this particular case, that will combine to make 14 waters. And everything else will remain the same here. And what will typically happen at this point is once you combine to make the water, you usually will have an opportunity to reduce down the water. So 7 waters here, we'll subtract off 7 from here and leave us with 7 waters. And that's going to leave us our now balanced equation here in basic conditions. So we should have 7 waters plus our Cr2O7 2 minus plus our 6 iron 2s, our 6 iron 3s, plus our 2 Cr3 plus, and we are left with just 14 OH minus. And again here, if I did not screw anything up here, this should be the balanced redox reaction in basic conditions. And it should still be balanced just like the acidic one was. We should still have the same number of elements on each side. So again, if we quickly look at it, we got 14 H's on the left, 14 on the right. We got 7 and 7 oxygens on the left and 14 on the right. We got 2 chromiums on the left, 2 on the right, and lastly, 6 irons on both sides. So our equation is balanced. Overall charge, if we look at the overall charge on the left-hand side, we got 0 plus a -2 and a plus 12. That gives us, I think, a plus 10, if I'm not mistaken on that. On the right-hand side, we have a plus 18 and a plus 6 and a minus 14. So again, that's a lot of math there, but that's like a plus 24 minus 14 is a plus 10. So again, it is balanced both ways, both in terms of charge and elements. And by the way, we know that this is now balanced in basic conditions, because if you look at the reaction, I no longer see H plus in it, but I see our good friend OH minus. Yeah, so we know this is definitely basic. Just like over here, we had H plus, which tells us it was acidic. Any questions on those steps to balance a redox reaction? All right, so I'll just scroll through this. This is pretty much what we just did, the one we just did. So in case you want to see it later, you can. I think it's actually on your paper, if I'm not mistaken. So why don't you try one here? Why don't you give this one a go? So take a few minutes here or get started on it, and then we'll talk about it. Balance this one. We're looking in, what are we doing here? Basic conditions, I think, right? Yeah, in basic conditions. All right, so balance it up. Try to make sure you figure out everything, like what is being oxidized, what is being reduced. Take a few minutes or so, and we will talk about it. Okay, so let's take a look here and see how you're doing, how you're progressing. All right, so we have this unbalanced equation here. So again, really the first step you would kind of want to do, or one of the first steps, is essentially you want to just split it off into its two half reactions. And again, it's just going to really be, the two things that sort of look like they're related. So obviously we have I minus going to I2, and we have MnO4 minus going to MnO2. Again, also a good idea to sort of try to figure out what is going on in terms of oxidation and reduction. So again, we could just kind of use our little number line thing here. And if we look at the iodine, it's going from -1 here to 0. So again, if we just kind of put it up on our number scale here, -1 is like here, 0 is going to the right, and going to the right means that this is going through oxidation. By default, the other guy is going through reduction, but might as well take a look at really what is going on there. So we essentially have MnO4 minus. So that's -2 for our oxygen. That's -8. And overall charge is -1. That means here we are looking at a +7 for the Mn on the left-hand side. On the right-hand side, we have MnO2, again, -2 for the oxygen. That's going to be a +4. So for our Mn, we're starting at like +2, which is like over here. And we're ending at +4, which is heading in this direction, which means it's going through reduction in this case. So again, that's sort of a fairly simple way you could kind of determine it. And again, it's good to have that in your head. That way, you know, kind of when you get to the part where you add the electrons, you know really which sides you should be adding those to. That also means, again, here our I minus, which is going through oxidation, would be our reducing agent, and our MnO4 minus, which is going through reduction, would be our oxidizing agent in this particular case. At that point, we want to balance everybody except oxygen and hydrogen. So we do need to put a 2 here in front of the iodine. And in terms of the Mn, we have 1 on each side. So we do not have to worry about it. Now, in terms of oxygen, which would be the next thing we want to do, the top one there has no oxygen, so we don't have to worry about it. Bottom half reaction there has 4 oxygens on the left and 2 on the right, which means to balance the oxygens, we would have to put 2 waters there on the right-hand side. Again, remember that for every water we add, we do need to add 2 H pluses to the other side. And that means in this case, since we added 2 waters, that is 4 H pluses that we do need to add to the left-hand side. Any questions on that so far? So again, here, I'm just going to kind of rewrite it so I could kind of see it a little bit better. So we have 2I minus goes to I2. On the bottom there, we have 4H pluses plus our MnO4 minus goes to MnO2 and 2 waters. All right. At this point, now that we have balanced everything, all the elements, the next thing that we want to balance is the charge. So we're looking again, not to get it to 0 on both sides, but to get it to the same number on both sides. And the only way we could change the charge is to add electrons, and those are negatively charged. So whichever side needs the negative charge added to it. The top half reaction there has -2 on the left and 0 on the right. Again, -2 from here and 0 overall charge here. That means that we do need to add a couple of electrons over here on our right-hand side. That's going to give us now a -2 on the right and a -2 on the left. Also makes sense. Again, this was our oxidation half reaction. We added our electrons to the product side, so that makes sense. Going on our bottom half reaction, we got a grand total of +3 happening on the left-hand side, and that is from +4 from the H's and -1 here from the MnO4 minus. Right-hand side, we got 0 happening there. Again, nothing has a charge on the right-hand side. So that does mean that we need to add 3 electrons here to the left-hand side. And again, that gives us -3 for the electrons, -1 for the MnO4. That's -4, and +4 is 0 on the left-hand side to match the 0 we have on the right-hand side. Again, also makes sense here. We added the electrons to the reactant side, as that is our reduction half reaction. Any questions on that there? All right, so we're ready to add these together, but again, we need to make sure we have the same number of electrons in each half reaction. In this case, we don't. We have 2 in one and 3 in the other. So we're actually going to need to multiply both half reactions by a common number. So we'll multiply the top one by 3, multiply the bottom one there by 2, and I'm just going to rewrite it on the next page there. So I can kind of see what's going on. So we'll carry that 3 across there on the top, and that will give us 6I minus goes to 3I2 and 6 electrons. On the bottom one there, we'll carry that 2 across the bottom one, and carrying the 2 across the bottom one there, we're going to get 6 electrons and 8 H pluses. So we have 6 electrons plus 8 H pluses. And again, carrying that to 2 MnO4s. And carrying the 2 to the other side and going the right way. There we go. 2 MnO2 and 4 waters, looks like. 2 MnO2 and 4 waters. If I copied that correctly, it looks like so. At this point, we're good to go. We can add these guys together. We're going to cancel out the electrons, which should cancel out. And I think that's everything at this point. So that's going to leave us 8 H pluses and 2 MnO4 minus and 6I minus. So that's everything on the left-hand side of the arrows, and everything on the right-hand side of the arrows also stays there. So 3 of the I2s plus 2 of these guys and 4 waters. Now, technically speaking, this would be our balanced equation in acidic conditions. So again, even though we're going for basic here, we could do everything in the acidic sort of way. But now that we have it in our acidic way, we can now do our basic part of the calculation. And here we're going to add 8 OH minuses to both sides. Again, we're going to do that because we have 8 H pluses. Also, why we know this is acidic, because we have the H plus still there. So again, we're going to add those H pluses to both sides, our OH minuses to both sides. So that would give us 8 OH minuses plus 8 H pluses, 2 MnO4 minus plus 6I minus, going to our other side here, 3I2 plus 2 MnO2 plus 4 waters, and our 8 OH minuses here. Just like we talked about before, these guys right here will then make 8 waters, and usually at that point you will have some waters you could get rid of. So we have 4 waters on the right. That will then reduce this guy down to 4 waters, and now we should be good. Let's just kind of clean it up here. So we have 4 waters plus our 2 MnO4 minus plus our 6I minus goes to 3I2 plus 2 MnO2 and 8 OH minuses. And again, if we did everything correctly, this guy should be balanced both ways, both in terms of both in terms of elements and also charge. So we have 8 H's on the left, 8 on the right. We have 4 and 8 oxygens on the left, that's 12. We have 4 and 8 on the right, that's 12. 6 iodines on the left, 6 on the right, and 2 MNs on both sides. Overall charge happening here on the left, 0, -2, and -6, so that's a -8. Overall charge on the right, that is 0, that is 0, that is -8, which is -8. So we are good. This is balance. Again, we also know it's basic because looky, there's our hydroxide that is there in this equation, just like we know this was our acidic one as we had H plus present when it was all said and done. Any questions on any of those steps there? All right, so why don't you try one more just to make sure here. Tell you what, let me skip that one. Let's do this one. So why don't you do this one in acidic conditions? So take a couple minutes, see what you come up with here. Okay, so let's take a look, see how you're doing. So same approach here. We're going to really just split this off into some things that look like they're related. So obviously this has got a chromium in it and probably should go with our chromium. This is our oxalate here, has carbon in it, and CO2 also has carbon as well. So we have our two half reactions here. We also perhaps want to figure out what is going on. So again, earlier we saw that the chromium here is +6 and our chromium is +3. So again, just like we saw earlier, chromium is starting at +6, which would be over in sort of this region, and it's going to +3, which would be meaning it's moving to the left. So that means that it is becoming more negative. So it is actually being our reduction here. By default, that would be our oxidation. And just to kind of make sure, oxygen going to be -2. There's 4 of them. That's -8. Overall charge is -2. There are 2 carbons, and that means each one should be +3, perhaps, right? +3 gives us a +6. And yeah, so far on the right hand side with our CO2, that's going to be -2, and that's going to be -4, which means our carbon is going to be +4. So in terms of the carbon, it is going from +3, which say what's here, and ending at +4, which is moving in this direction, and that is going through oxidation. So that does make sense. Any questions on that? Again, what that means is our dichromate here would be our oxidizing agent, and our oxalate here would actually be our reducing agent, right? So now that we have it split off, now that we have a pretty good idea, obviously, what is being oxidized, what is being reduced, next thing we want to do is balance every element other than oxygen and hydrogen. So we have 2 CRs on the top, on the left, and 1 on the right. So we do need to put a 2 in front of the CR. On the bottom, we have 2 carbons on the left and 1 on the right. So we actually need to put a 2 there as well. Next, we want to move on to oxygen. So top guy on the left there has 7 oxygens, none on the right. So we are going to put 7 waters over here. Because we did our 7 waters, we do need to put 14 H pluses to the other side to balance out the hydrogens. On the bottom, we have 4 oxygens. By putting the coefficient here, we actually got 4 oxygens as well on the bottom. So we actually don't need to add any water to the bottom, because by balancing the carbon there, it did balance out our oxygen as well. Any questions on that so far? So again, I'm just going to kind of rewrite it because I'm going to need to add some stuff to it. So we'll do 14H plus Cr2O7 2 minus 2Cr3 plus and 7 waters. Bottom here, C2O4 2 minus and 2CO2. At this point, we're now ready to add our electrons. So overall charge happening on the left, on the top one there, we got like a +14 for the hydrogens, a -2. That looks like a +12 happening over there on the left-hand side. Right-hand side, +6. So left-hand side here is going to need 6 electrons. Again, does make sense. We're adding it to the reactant side. This is our reduction half reaction, so that's all good. Bottom guy, we got grand total -2 on the left and 0 on the right. So right-hand side here needs a couple of electrons. Also makes sense, again, adding electrons here to our product side in our oxidation half reaction. So we're looking good here. We're almost ready to add them together. We do need to multiply the bottom half reaction by 3, and that is to get our electrons to be the same in both half reactions. So if we do that Again, just sort of copying it over so we can kind of see it a little bit clearer, hopefully. So nothing changed on the top one. The bottom one there, we're going to distribute that 3 all the way across. So that's going to give us 3C2O42 minus, gives us 6 CO2 and 6 electrons. We are now good to add those together. 6 electrons here and here will cancel. And I think that is it. So we are down to 3C2O42 minus and 14H pluses, and our dichromate. And I think that should take care of everything on the left-hand side of the arrow. On the right-hand side of the arrow, we have 2 of the Cr3 pluses. We have 7 waters. And lastly here, 6 CO2. And again, we should now be balanced in acidic conditions. We do see H+, so that tells us acidic. So just quickly surveying everything here, looks like we have 6 carbons on the left. We have 6 on the right. We have, looks like 3 times 4 is 12 oxygens and 7 more. That's like 19 oxygens on the left. And on the right-hand side, 7 oxygens and 12 is 19. 14 H's on both sides and 2 Crs on both sides. Overall charge on the left-hand side, 3 times minus 2 is minus 6. And minus 2 for the dichromate is minus 8. And our plus 14 is like plus 6, it looks like. And on the right-hand side, plus 6. So we are definitely balanced here in acidic conditions. Any questions on how to balance redox reactions in basic conditions, acidic conditions, how to identify what is being oxidized, what is being reduced, what's your oxidizing agent, reducing agent, oxidation states? Any questions on any of that stuff there? Again, sometimes the best thing to do on these things is to go slow. And when you recopy something, make sure you recopy it correctly. Sometimes people kind of screw it up at that point. Any questions on any of that there? Okay. So we're then going to talk about kind of the main part of this chapter then is kind of putting these together. And we're going to talk about galvanic cells. And really galvanic cells are really nothing more than sort of redox reactions that take place. And this is basically what a galvanic cell looks like if you were to build one perhaps in the laboratory. And in the laboratory, you know, you would have a couple of beakers. You would also have some electrodes here. So you got some solid electrodes. And typically, whatever the solid electrode is, so for example, this side here is zinc, you typically would have the solution that would contain the zinc ion basically floating around in it, and another kind of spectator ion there to kind of balance out the charge. And same thing over here. This is copper. And we see in the actual solution, we have copper ions floating around. So it's really important sort of in a galvanic cell that in the solution part, you obviously have the ions that are part of the reaction really and the solid electrode. Now there's 2 parts to a galvanic cell. So here on the left-hand side, this is the anode side. And at the anode side, that is where oxidation occurs. So anode side, oxidation occurs, which basically means we're going to lose electrons. And that's what we see here. So in this process, what's going to happen is our zinc is going to start out in the solid. And basically it's going to lose an electrons. And when it loses electrons, that solid zinc basically jumps out into the solution and goes for a swim. And those electrons that the zinc loses in this particular example can travel through this wire, go through a voltage meter, and you'll get a voltage that will occur. And the electrons can travel to the other side. And on the other side of a galvanic cell is the cathode side. And as it says there, on the cathode side of the galvanic cell, that is where reduction takes place. and you actually gain electrons. So what happens in this, if we sort of super zoom in, is as those electrons come in from the other side, they will actually combine with our ions that are floating around in the solution. And basically those ions in the solution then will pop out of solution and sort of become solid copper in this particular case. So on the anode side, you have these solid guys losing electrons. And when they do, they basically become ions and go for a swim. Those electrons then travel through the wire to the other side where they combine with the ions that are in the solution. And those guys gain those electrons and they basically go from an ion that's floating around to a solid that basically will come out of solution as well. As we'll talk about, those electrons that are basically traveling around can be used for some type of work. It's sort of very similar to how like a battery works. Those electrons go out and they power your device and so forth. What sort of connects both of these sides of the cell is what is referred to as the salt bridge. So the salt bridge usually will contain some type of salt, obviously, right? And a salt is an ionic compound. So in this particular example, we have the chloride, potassium chloride. And as you can see, what ends up happening is the potassium ion starts dropping down to this side. The chloride ion really drops down to this side. And you may say to yourself, why would that happen? Well, the salt bridge is there for a couple of sort of reasons, but the salt bridge is really there to kind of keep this reaction going. And what I mean by that, for example, is if we just think about what's happening on sort of both beakers, if you will, right? When the oxidation occurs in the zinc side, we are basically dropping positive ions into that solution. So we're building up a lot of positive charge here by dropping those zinc ions into solution. Same thing happening over here on the right-hand side. When that copper gains those electrons, those positive ions are actually leaving, right? They're actually leaving and going into the solid phase over here, which means we're ultimately building up a lot of negative charge, oddly, in here. And if we didn't have this salt bridge here to kind of keep the charges in balance on both sides, the electrons would no longer have a need or a desire to go across to the other side. Because ultimately what's keeping the electrons kind of moving to the other side is what is known as the potential difference. Simple way to think about it is this side is kind of more positive, right? Negative electrons kind of attracted to the more positive side of the cathode. But if you don't have anything connecting these two sides, you're going to build up more negative and negative charge on the right-hand side. And my negative electrons are going to go, no, thank you. I don't want to go that way anymore. I would rather go the other way. And this reaction is really not going to continue to take place because there's no need for those electrons to go to the other side because it's already negative. So by having the salt bridge in there, what we see happening is as we're building up the negative side over here on the right-hand side of the reaction, those positive ions from the salt bridge, like the potassium ions, start to drop in here. And what that's going to do is bring down that negative charge that's building up and kind of keep it a little bit higher on the positive side and continue to bring those electrons to the other side. Same thing's happening over here. The negative chloride is dropping into here and kind of getting rid of that buildup of positive charge it's going to get if the chloride wasn't there. And again, what that's going to do is keep that potential difference between the anode side and the cathode side, really keeping the cathode side a little bit more positive, and that's going to help drag those electrons really to the other side. So really the salt bridge sort of keeps a control, if you will, on the buildup of charge that would occur. So again, without that salt bridge there, those charges would build up on both sides, positive and negative, and eventually the electrons would really stop flowing from one side to the next. So with that electrolyte or that salt solution in that salt bridge, by moving those ions into both sides, it's able to keep the charges relatively balanced the way they were to begin with probably a little bit more positive charge happening on the cathode side. Again, that's that potential difference that's able to draw the electrons to the other side. Any questions on that there? So when we look at this, again, it is really a redox reaction. So here is our oxidation half reaction, our zinc going to zinc 2+, which means it's losing a couple of electrons, so being oxidized. This is our anode, our cathode reaction, or reduction reaction. Those 2 electrons that are lost by the zinc gets picked up by the copper 2, and it gets reduced to copper solid. Adding both of those half reactions together, we get the overall reaction that's taking place in here. The overall net ionic reaction that's taking place is zinc is going from no charge to +2 when it loses electrons, and the copper is saying thank you very much. The copper with the +2 charge is picking up those electrons and going to solid copper. Any questions on that there? So as I mentioned, really what's sort of driving those electrons to the other side is that sort of potential difference. And really, again, sort of a simplified way of thinking about it is the cathode side kind of more positive. So it's drawing those electrons from the anode side to the cathode side. And, you know, that's why a lot of times we have like positive, negative sort of symbols on like batteries and stuff like that to sort of indicate that. So we sometimes talk about this potential difference as being the cell voltage. The cell voltage is basically 1 volt is a joule of work per coulomb of charge. So a volt is equal to a joule over a coulomb. That's a unit of electrical charge. Sometimes they'll talk about that as the EMF of the cell, the electromotive force, or they'll just talk about it in terms of the cell potential, which is basically the force or the pull of those electrons from the anode side to our cathode side. So in problems, they'll sometimes ask you to calculate any one of those 3 things. They'll sometimes ask you to calculate, hey, what is the cell voltage? What is the EMF of the cell? What is the cell potential? Basically, in most cases, if they ask you to calculate any of those things, they're basically asking you to calculate the cell voltage, basically. So you're actually trying to calculate the cell voltage. There's a nice picture of a galvanic cell. Again, you can see 2 beakers. Again, this is probably the one we were just looking at. This is probably zinc ions floating around. The blue guy is our copper 2. Maybe a little hard to see. There actually is a little kind of tube that connects the 2 right there. And that is your salt bridge. Again, if you hook it up to a voltage meter, you can obviously see 1.1 volts. And we'll see positive voltage is actually a good thing here as well. Now, there's also another way that we commonly sort of represent galvanic cells, and that is what is referred to as the cell diagram. And the cell diagram is sort of a shorthand that is used to basically write a galvanic cell or write what's happening with a galvanic cell. And it basically is a couple of different parts to a cell diagram. And let's take a look at sort of how we get those parts. So basically, we start out with our anode side, and our anode side is our zinc. In this case, again, our zinc going from 0 to +2. So in terms of what's happening with our zinc, again, starting at 0, ending at +2, going to the right-hand side, so it's being oxidized. While our copper is starting at +2 and ending at 0. So starting at +2 over here, going towards 0, going to the left, is being reduced. So the anode, which is our oxidation, is our zinc. So the way this is our zinc, and this is really our reactant, and this is our product. So sort of our reactant and our product sort of separated by a line here in our anode compartment. You will also sometimes see things written in here like the concentration is 1 molar. Sometimes people don't write it if it is 1 molar. There's also a potential that there could be gases involved. So sometimes you'll see pressures written there as well. We then have kind of 2 lines here, and these 2 lines represent the salt bridge. And then we get basically to our cathode compartment. And in our cathode compartment, this is basically our reactant separated by a line to our product. So that's usually the general sort of setup for a cell diagram. It's always anode to cathode. 2 lines kind of separate the anode and cathode compartment. And again, if you're given just a cell diagram here and you needed to get the reaction from it, this is basically how you would do it, is what we just talked about. So basically here, we would start with our anode side. And again, the first thing there would be our reactant. So you would write zinc. The second thing would be our product, which means our zinc would go on the other side over here with a +2 charge. Then we would go back to our reactant here. So it would be plus our copper with a +2 charge. And again, this would be our product, which would be over here. So again, you do need to be able to kind of go from the cell diagram to the equation, and obviously vice versa from the equation to the cell diagram. So again, it's always that way. And obviously one should always have a charge. So obviously like the zinc there with the +2 should have a charge. The copper with the +2 on the other side should also have a charge. And again, you could kind of see just from the cell diagram, zinc going from 0 to +2 being oxidized, copper going from +2 to 0 being reduced. Any questions on that there? Okay. I think we will lay it up there for today in terms of lecture. It's probably a good stopping place, I think. We will continue on Tuesday. And I think we got a couple more weeks, I think, until the exam. And I think the next exam will cover through this chapter. So we have all next week. So I think we should hopefully get through this chapter by next week. So we should be on schedule on that. Again, a reminder today, we are continuing on with titration experiment. So again, you can use that time to work on the 3 parts of the experiment. And again, in terms of schedule change, I know it says we're going to start the oxidation reduction reaction on Tuesday of next week. So I think we'll continue to maybe work on the titration one as well. I'm not sure we'll start the oxidation reduction one on Tuesday next week. Maybe we'll start just on Thursday. All right. Make sure you put here if you haven't done so, and I'll see everybody in about 20 minutes.